Alright students, so this is our last video related to pure vibrational spectroscopy. And in this video, we're going to revisit a topic that we briefly mentioned back when we talked about our harmonic oscillator, which feels like forever ago. So when we talked about our harmonic oscillator, we briefly mentioned that real molecules are actually anharmonic oscillators. So in this video, we're going to talk about anharmonicity. So let's remind ourselves a little bit about harmonic oscillators and anharmonic or real oscillators. So if we plot the potential energy versus internuclear distance, R, or bond length, right? R is also could be called bond length. Our harmonic oscillator looks like a parabola. This isn't a very perfect parabola, but it should look like a perfect parabola with a function kx squared divided by 2. And if we looked at if you remember, our Morse potential or our more realistic potential for an anharmonic oscillator looks something like this blue curve. So it spikes a little higher in potential energy as R gets small, or as the bond compresses and the nuclei come close together, and it flattens out and reaches, a plateau value at large R. Do you remember what we said those things represented? So as the nuclei get really close together, we have pretty intense Coulombic repulsion between the positively charged nuclei. So that is why we have a steeper increase in potential energy at small r values or small internuclear distances. What happens at large internuclear distances is we keep pulling the bond apart. The bond dissociates, right? This would be breaking the bond. So that plateau value actually represents a dissociation energy. So another thing we can talk about here is the spacing of our vibrational energy levels. And so we think about the harmonic oscillator. Remember, those energy levels were perfectly and evenly spaced all the way up the parabola. But that's not going to be true for our anharmonic oscillator. It turns out that for our anharmonic oscillator, they start out the same, but then the energy levels get closer and closer together as they get higher in energy. And so eventually you get a whole bunch of energy levels clustered together, basically on top of each other, at that dissociation energy or that plateau point. And again, often this dissociation energy is written as capital letter D. So that would be your dissociation energy would be from the bottom of the well, right, the bottom of your potential energy curve, to that plateau. And so if we think about an anharmonic oscillator, one way of getting to what we call a Morse potential or any other type of real anharmonic potential energy curve is to take our function for potential energy, V of R, for a real oscillator, and write it as a Taylor expansion about the equilibrium bond length, which we call R sub E, right? So with our harmonic oscillator, we called this x equals 0, right? We said that this was 0. It's also sometimes called R sub E, which would just be the equilibrium bond length or equilibrium internuclear distance for two atoms. And so we can write this Taylor expansion. It would be V of R minus our equilibrium potential. And it's going to give us something that looks like this. We get a squared term, right? We get k over 2x squared, which we're familiar with. Then we get a cubic term, so we get this gamma sub 3 divided by 6 times x cubed. Then we get gamma sub 4 over 24 x to the 4th, so we get a quartic term, and we technically could get infinite terms, but in theory each of these terms gets smaller and smaller and smaller, and so it's normally fine to truncate this series pretty early on. Although truncating it after the very first term and calling it a harmonic oscillator can often cause issues. Often that's not a good enough approximation, and so we have to include either just the quartic term or either just the cubic term or the cubic plus the quartic term. All right, so K, remember, we called that our force constant, and it was related to bond strength. Gamma 3 goes by several names. It's not always written as gamma sub 3, but it would be our cubic force constant. And gamma sub 4 would be our quartic force constant. And these are also related to bond strength, right, in some way, shape, or form. We're a little less familiar with these, but they are also related to bond strength. But they also give us information. The bigger those terms are, the less harmonic the bond behaves as. All right, so this K/2 we said was familiar. We could think about this in our perturbation theory terms as the 0th order term for the potential energy operator within our Hamiltonian. So this would be V hat 0, whereas the cubic term we would call V hat 1, and the quartic term we might call V hat 2. And these would be our first order and second order perturbation terms to the potential energy operator. If we only include the 0th order term, so no perturbation, we're thinking about a pure harmonic oscillator, we get a transition energy of delta E, representing the change in energy as you go from quantum number nu1 to quantum number nu2, as h bar, the square root of k over mu, where mu is that reduced mass, v2 plus 1/2, minus h bar, square root of k over mu, v1 plus 1/2. Because individually, h bar, square root of k over mu, nu plus 1/2 is simply the resulting energy for a harmonic oscillator from the Schrodinger equation. And so we can combine that to say h hat, square root of k over mu, v2 minus v1, which we've seen before and we've used this equation before. However, you might recall from lab, spectroscopists love wave numbers. In fact, we have our instruments report infrared spectra in wave numbers directly, and sometimes we don't even call them wave numbers, sometimes we accidentally call them frequency. But c'est la vie, we love wave numbers, so let's convert some things to wave numbers. Remember that energy can be written as h nu, where nu here is the frequency of light, not a quantum number. But nu can also be written as c over lambda, so we could have E equals hc over lambda, and 1 over lambda is wave number. So really energy is equal to Planck's constant times the speed of light times wave number. So we can convert energies into wave numbers by dividing our energy by Planck's constant times the speed of light. So let's go ahead and do that. So we can write this now as delta nu tilde, which would be our change in wave number representing the transition from quantum number 1 to quantum number 2. And we could write this as h over 2 pi, because that's what h bar represents, 1 over hc, square root of k over mu, v2 minus v1, nu2 minus nu1, sorry about that. And then we could simplify that to simply 1 over 2 pi c, square root of k over mu, nu2 minus nu1. And this is the equation you actually used in lab, and you wrote about hopefully in your oscillator lab report. All right. If we go back, and now we include the cubic and the quartic terms, that potential energy operator, we can get a different result. So the first result I'm giving you here is simply the wave number associated with a single quantum number state, so not a transition. We get nu tilde, which is our wave number, equal to nu tilde sub e. We'll come back to that. Nu, this time nu is our quantum number plus 1/2, minus x sub e tilde, nu sub e tilde, times nu plus 1/2, where again this last nu that doesn't have a tilde is our quantum number. So nu sub e tilde is our constant, 1 over 2 pi c, square root of k over mu. So that first term is actually just the harmonic oscillator result for wave number. X sub e tilde is what we call our anharmonicity constant for a particular bond. So within a single molecule, all the bonds can have different anharmonicity constants, right? Each bond is unique. So it can have a unique anharmonicity constant. So xe tilde is our anharmonicity constant. You'll notice it's multiplied back by the first term. And those two results are subtracted. So we're getting sort of this small correction, which is decreasing the wave number. And wave number is directly proportional to energy, so it's decreasing the energy. So it's explaining why those energy levels get a little bit closer and closer and closer and closer together as we go up in quantum number or go up in energy. And so let's convert this to a transition wave number, because that's what we actually measure with a spectrometer, right? Is this transition. We can convert this to transition by simply taking nu2 minus nu1, because we'll really have nu2 plus 1/2 minus nu1 plus 1/2, which is going to give us nu2 minus nu1. And our constants out front stay the same, so we get this equation here, where we have nu e tilde, nu2 minus nu1, minus x e tilde, nu e tilde, nu2 minus nu1, whatever nu2 and nu1 happen to be. And when we include the cubic and the quartic terms, it actually also changes our transition dipole moment operator a little bit, and it changes our result, right? So it will change our wave function, it will change everything just a little bit. And we're not going to work through all the calculus to get to those results. We're not even going to show you most of the results, but what I am going to show you is the change in selection rule. So both for Raman spectroscopy and infrared spectroscopy, they had one selection rule in common, right? All vibrational spectroscopies have the selection rule that delta nu is equal to plus minus 1. So that quantum number can only change by 1 for an allowed transition. When we include the cubic and the quartic terms, that's no longer true. In fact, we can have any value, any integer value, positive or negative, of delta nu. So we can change by 3, or we could change by 11. But there's a caveat here. This anharmonicity constant is normally very small. And so you're going to end up with the delta nu plus minus 1 as being a really large peak, or the largest peak. Maybe it's really small to begin with. Then you're never going to see anything else. Because delta nu plus or minus 2 is going to be much smaller than the delta nu equals plus minus 1. And the delta nu equal to plus minus 3 is going to be even smaller than delta nu plus minus 2, etc. So these are going to decay very rapidly with intensity as you increase your delta nu, or the spacing between the quantum numbers. So the last thing I want to mention in this video, because your book is going to use this quite a bit, and I have a habit of using it, and so I want to make sure I give you some nomenclature rules for vibrational spectroscopy. So vibrational spectroscopy nomenclature. The most important transition and the largest peak is always represented by the 0 to 1 transition for a specific motion of a specific bond. And so for that specific, say we have a carbonyl stretch, its largest peak, around 1700 wave numbers, would be called the fundamental transition, and it would represent the nu equals 0 to nu equals 1 transition for that bond. The nu equals 0 to nu equals 2, which will be much smaller, is always called the first overtone transition. And so the peak, or the vibrational band, whatever you want to call it, peak and band here are synonymous. That peak that represents this first overtone transition is often called the first overtone peak. The V equals 0 to 3 would be the second overtone, and we could go on, right? So why do we always start with the assumption that the molecule is in its ground vibrational state for all vibrations? So why do we always assume that we start with nu equal to 0? Because technically that's not part of our selection rules, right? So the reason is that thermal energy, or temperature, is not generally large enough contributor to excite a molecule vibrationally. That's not going to be true when we're dealing with smaller energies like rotation, but thermal energy, or simple heat, cannot excite a molecule vibrationally with significant statistics, right? So the most probable possibility is that every molecule and every motion, vibrational motion within that molecule, starts at quantum number 0. All right, so in the rest of the videos for today, we're going to be dealing with our first hybrid spectroscopy, which is going to be vibronic spectroscopy.